My name is Greg Moore. I'm a teacher with New South Wales TAFE. If you've only just caught up with us regarding these series, we're doing homework for a subject, DC circuits, UEENEEE104A. And this would be the fourth lot of homework that's been set, and this is the video solution for that homework. This particular homework was quite involved. Everything was going well in DC up until we hit parallel, and then of course, like always, things get a little bit more complicated. But nevertheless, we'll work our way through. The homework had around about 13 or 14 questions in it, and some questions were easy, but perhaps not too many. Some of the questions required a lot of working out. I sat at my desk at work and worked my way through, and probably took me about, probably took me 3/4 of an hour or something to get through it. Maybe a few interruptions in between. So I'm guessing that students took a lot longer to do the homework. So anyway, page 1. Here we are. It's 2018, just in case this video is around for a long time. And this was version 1 of the homework. There'll be many more of these to come in the future. Question 1, determine the resistance of the following circuit. So when you first look at it, you see 3 resistors in parallel, and you see one that looks like it's in series, but in fact if you swing that around and put it up here, it's actually in parallel with the other resistors. So we've got 4 resistors in parallel, but be careful, one is 270 ohm, the other 3 are 220 ohms each. 3 lots of 220 ohms, you don't really need to apply the sum of reciprocals there. You can simply go R divided by N, the resistance divided by the number of the identical value resistors, because don't forget they have to be identical. So 220 divided by 3, 73.33 ohms, and then we had a further 270 ohm in parallel, so the sum of the conductances here, there's the 73.33 from the first 3, there's the 270 from the last one. The absolute total equivalent resistance of that circuit is 57.66 ohms. If one of the 220 ohm resistors becomes open circuit, what's the new total resistance? Well, that would simply be 220 divided by 2, because there's only 2 of them now. It's gone open circuit, so it's just like I got the cutters and I cut that wire. It's like disappeared from the circuit. What's the new total resistance? So 1 on 110 plus the 270 on the end, 78.15 ohms. Increased quite a bit from the 57 ohms that we had there originally, because the more parallel resistors that we have, the lower that resistance goes. Take 1 or 2 out of the network, the parallel network, and the resistance will increase. If one 220 ohm resistor becomes short circuit, what's the new total resistance? Hey, if you put a short circuit across any one of those, if you join that with a piece of wire there, so if you put a link of wire across there, you'll have a short circuit across all of those, and of course you'll have 0 ohms. The next question, what's the colour code for the 270 ohm resistor? This was probably the only really easy question in the whole test. Red, purple, brown, if it's a 4-band resistor, and of course then it would have either, I don't think you can get resistors with no tolerance band on the end meaning 20% anymore. They were like the old mud carbon resistors, and they're long gone, so now it would be a silver band, maybe even silver's disappeared now, 10%. It'd be 5%, which would be gold, or maybe red, which would be 2%. Question 5. What's the difference between a Category 2 multimeter probe and a Category 1 multimeter probe? Cat 2 is rated at mains voltage, but Cat 1 is for circuits not connected to the mains. So be very careful if you're using a digital multimeter, or any multimeter for that fact. Check what it says on the probes, and if they're not Category 2, don't go probing around 240 volt circuits. And in fact, if you want to work on switchboards and distribution panels, you've got to go higher again to a Category 3 meter to be entirely safe. Category 3 probe or meter. All of these probes, they've got a reasonably high working voltage, But it's the transients that get you, and the transients, I think for the Cat 1 even go up to about 1,000 or something volts. Transients for the Cat 2 are higher, but the main thing is their Category 2 is rated for mains voltage. That's what I was looking for. The next question, question 6. We've got a big question here. Just looking at it, we've got 3 resistors in parallel, 2 resistors in parallel, and 2 resistors in series with the whole circuit. I've added a small earth over here as a reference point off the negative side of the battery. I've said first solve this, and I've used the sum of conductances there, 56.42 ohms for that network. This network, I solved 60.44 ohms across there. Then adding all of those networks together, that network, and the 2 single resistors in series, 220, which is this one here, 60.44 ohms, which is this, 56.42, which is this, and 470 ohms on the end, 870 ohms all up. Determine the voltage shown on the meter. Yeah, well look, that's a bit more complicated question, because we can't answer that before we work out the current flowing in the circuit. And that voltage is across just this network here. So it's across the 56.42 ohm resistor. Question 8 then, we said that we had to know the current first, so I equals V on R. It's 88 volt battery, and we've got 807 ohms total that we calculated, so that gives us 109 milliamps. So the voltage shown on the meter, I guess we're going to have to go to the other sheet, and that's down here. Question 8, there's our 109 milliamps again. The previous answers we saw on that homework sheet. Question 7, you had to do question 8 first. We know that now. That was the current. But then this particular question, and I can see I've probably got a small mistake here already. All right, I've drawn this as a voltage divider. So the voltage across the meter, question mark, we've got 88 volts on the supply rail. And then 220, 60, 56, 470 ohms. And for a voltage divider, the rule is the supply voltage multiplied by R2 over R1 plus R2. R2 is the bottom resistor. Now, you're going to say, but there's more than 2 resistors here. There's 4 resistors. So what do? Well, I group these because I want the voltage across here. And I think I've made a little mistake here. I think that I only asked for the voltage across that. But we'll see how we go with the maths. Maybe I've just drawn that wrong. I'm not sure. Divided by R1 plus R2, so it's a ratio. So the sum of all of the resistors as the denominator just into the R2, what we're getting the voltage across here on the bottom. I had to work out what R1 and R2 were by adding these groups of resistors together, and that gave me these 2 values. And then I was able to use those in the equation to get 57.4 volts. But I can see already I've got 57.4 across this part of the network, this part of the voltage divider, and it was asking me for the voltage across this resistor only. So I've actually gone one step too far. I didn't really have to do that. Once I had the current flowing down through this chain of resistances, I could have just V equals I times R, got that 109 milliamps and multiplied it by 56.42 ohms. So if you have looked back at the that other page, I can just jump back to it here. Yeah, look, I went a bit funny here, and I thought that probe was on the ground, but it's actually across this last network, 56.42. So just a little bit different there in solving that. But nevertheless, we might need this voltage divider for another question later on. Question 9 was the power dissipated in the 330 ohm resistor. What I've done here, because I've got this block of 4 resistances in series, all in series, you know, I've put them as a rectangular block. And there's my 88 volt battery, 109 milliamps of current flowing down through it. And then because it's asking me about the 330 ohm resistor, I've only mapped this part of that block. And remember, this block had this 56.42 ohm is actually the REQ of this. You can see it again there, 56.42. And we need to use the current divider rule here, because if I need to know the power dissipated in the 330, and there's a couple of different ways I could do this. I could use Ohm's law for it, but I tend to use the current divider rule for just about everything. IRX equals REQ over RX times I network. So I network is the current flowing into that network, 109 milliamps. And then REQ is 56.42 divided by the resistor I want to find. In this case, 330 ohms, 18.63 milliamps. I find that just very, very quick to do. Sometimes there might be an occasion where I'll use Ohm's law, but most of the time I use that. Now, we've got to take that to a power. Again, here we could use P equals V squared on R, P equals I squared times R, P equals V times I, but P I squared times R, because we already had the current, so it's 18.63 squared times just that resistor, 330 ohms, to get 114.5 milliwatts. Question 10 and question 11. Let's just go back and read what it says. It looks like it says something about taking the 330 ohm resistor out of circuit, does it? 10 and 11. Question 10 and question 11. Question 10, if the 330 ohm resistor becomes open circuit, find the new voltmeter reading. Ooh, so that's going to change the dynamics of this part of the network. If we take a resistor out, we're going to increase the value of that slightly. So let's jump back down and have a look at that. All right. We previously had 56.42 ohms in that network. We saw that again on the last question. But now the new REQ, I've only got the 91 and the 470 in because I have cut that little critter out of circuit. So 76.24. And I've done a case 1 here and a case 2. You see, I've done a nice block of resistance here again. We had the entire resistance being 807. And now case 2, I need to find out what the new resistance is. Well, because this is about 20 ohms higher than that first one, we had 56.42, 76.24, close to 20 ohms higher. There it is there, 827 ohms versus that 807 ohms that we had originally. So the current, 88 volts divided by the new resistance, 827, 106 milliamps. And you can see that current there is slightly lower than the original. I think we had 109. We had 109 milliamps there before when the circuit was in good condition. And because the resistance in the circuit increased just a little bit, now we're up. We've dropped the current down a little bit lower. Question 10. Question 10 says, what's the voltage going to be across that new resistor? Well, again, I've made the mistake. I've gone a bit cross-eyed or something there, and I've looked at the circuit and I've put the meter between that point and that point. Not a big difference. Again, this is actually easier to work out if I'd read the question right in the first place, because I've got a current coming down here of 106 milliamps. And then I can simply multiply that current by the 76.24 ohms, and then that would give me the voltage across that resistance. What I've done, I've used the voltage divider rule again. I've just split this up, R2 over R1 plus R2, and that becomes a ratio then to multiply the supply voltage by to get a voltage out of that. And I can do that at any point in a multiple tapped, multiple resistance type circuit. And I tend to sort of use this a lot, but if I'd read the question right, I would have done that slightly differently. All right, so question 11. Question 11, I actually made a small mistake. Those of you that were paying attention to the original circuit, it said, question 11, if the 330 ohm resistor becomes open circuit, find the new current meter reading. Oh dear. Look what I did. I sort of didn't read my own words. Here's the current meter. It's not talking about the circuit current. It's talking about the current meter. And the current meter is sitting here off the end of the 180 ohm resistor. So I went back into that and I redid that question. So question 11 redone. That's that beautiful current meter that I drew, and it's in line with the 180 ohm resistor. I got 106 milliamps flowing down through the network as we saw before, so not too much more to calculate here. Simple current divider again. The REQ of this network, 60.44 times the 106 milliamps coming in or out, if you like, and divided by 180 ohms, because that's the individual resistor we're looking at. Give me 35.6 milliamps travelling in that one. Of course, if we've got 106, the difference between the this one's got 35, that one would have to have 106 minus the 35, so around about 69 milliamps or something going down through that one. And that's what you'd expect, because that's a smaller value resistor, and the smaller resistor gets more of the current. Question 12. Question 12 says that we've got a short circuit, I think. Let's just go back and look at question 12. Question 12. The 180 ohm resistor suddenly became short circuit. The new current meter reading and the new voltmeter readings are. Ooh, okay. Question 12. Well, I made a little tiny mistake here as well, and I'll discuss this. We've got a short circuit that I've drawn across here, and I instantly said the current meter reading is going to be zip. But in fact, if the 180 ohm resistor was to have gone short circuit, I'd have the current running down through that piece of wire, still going down through the meter, and that would have 91 ohms across it. And that would be a bit of a mess, because if the meter had an internal resistance of like 20 ohms, because it's only a milliamp meter, so it could have a fair bit of resistance, then that 20 ohms would be in parallel with 91 ohms, and that would give me some really weird reading across that. If you put like that, would become a shunt, what they call a shunt resistor across the ammeter, and that'd be a really weird thing to think about. So yes, I did make a small mistake there. I went across the whole network, and it is worth thinking about that. A short across the 180 is a short is different to a short across the whole network. The way I've got it done, the meter would not deflect at all. You wouldn't get any reading. But if you short circuit the 180, you're going to get a meter reading, but it is not going to give you the total current flow for the circuit. It's going to give you some weird value because of that shunt resistance across it. And the voltage, the new voltage, because of that, well, we've got a different RT in the circuit now. We've taken this network out completely. Regardless, you know, pretty well where I've put that short, you just have to, I suppose, you know, for this next question, say that the ammeter had no resistance. It's a perfect ammeter. And then that network comes down to 0 ohms. So we're only left then with the 220 ohms, 56.42. There's my 220, 56.42, and the 470, which gave me 746.42 ohms, 118 milliamps. Lower resistance, higher current. And then we can work out, I've done it again using a voltage divider. Have to look closer at that circuit next time. And I got 62.06 from this point down to ground. But of course, if I'd read that circuit more correctly, I would have found out that I had, what do you got there, old son? I'm just doing some recording. Yeah, just dump it there. Yeah.
Sorry.
That's all right. No problemo. Okay, all right. So if I'd read that question correctly, we just had a word from our sponsor there. I would have had the current travelling down through all of those, and V equals IR. I could have multiplied that current times the 56.42 ohm resistor, and that would have given me the voltage across that one resistor. Question 13. What's question 13? The current meter in the circuit shown below is reading 110 milliamps. So look at this. We haven't got the battery voltage. We've got the meter coming off the end of the 47 ohm resistor and coming up to here. It's giving us a current reading of 110 milliamps. Find the reading on the voltmeter. Well, this is not... I mean, what we have to do here, obviously, we can work out the voltage across this network because I've got a resistance and I've got a current. So V equals I times R. And then I've got the REQ for that whole network with a voltage across it that I can work out the total current flowing, the Kirchhoff's current flowing in the entire circuit. Then I can multiply that current by individual resistances to get the voltage across. But of course, again, the voltage across this middle network. So let's jump down and see what we did for that. Question 13. Question 13, we've got 110 milliamps travelling through a 47 ohm resistor. I multiply it out, I get 5.17 volts. And in fact, that's all that was asking. It's asking what's the voltage across that network, and the answer was 5.17 volts. The total circuit current was 215.4 because the REQ is 24 ohms, and 5.17 volts divided by 24 gives me a total circuit current 215 milliamps. And then the next question, oh no, that's just the same one, isn't it? That's just 32, I see what we've done, 32.1.53 volts. That's what we had to find, the battery voltage, wasn't it? So we needed to find, after we got that total circuit current, we had to multiply it by all of the resistances added together, or you could multiply it times that, get that voltage, multiply it by that, get that voltage, etc., and add all the voltages up. Whichever way you do it, I got 32.53 volts across the battery. Question 15, it says something about using the same battery voltage. Yeah, we did question 14. Question 15, the last question, luckily, running out of time here. Using the same battery voltage you found in question 14, the 120 ohm resistor suddenly goes open circuit. Find the new current meter value. Oh, these get monotonous, don't they? So you've got to go back into the problem again, and now you're going to have new resistances. I've mapped it out, 91 in parallel with 168, 47 in parallel with 82 to give me an REQ of, now 29.9 ohms and 68 ohms on the end. And dividing that new total resistance, RT, into the 32.53, I get 207.3 milliamps. The 207.3 milliamps is coming down. It asked us for the new current in that meter, which is measuring the 47 ohm leg, and it works out to be 131.87 milliamps. All right, that's the end of the homework. There was a lot of questions there, and there's an awful lot of information to know. This is covering current dividers, it's covering Kirchhoff's voltage and current law, series parallel circuits, current dividers. It's covering a lot of stuff. So I wouldn't just look at this and say, oh, look, yeah, it's homework, it's not that important. Because, as we move on and we get into capacitor theory, and we're doing charging capacitors and series capacitors, capacitors in parallel, we've got the Wheatstone bridge to finish off in resistances yet. So don't neglect this. Spend the time to do it and make sure that you understand it. If you're not understanding it, you can email me, or you can see one of the teachers here, and the teacher will sit down with you and explain how it works. This has been Greg Moore for New South Wales TAFE. Bye. See you next time.